This video is for section 8.3, the converse of thy Pythagorean theorem. Let me just fix that. It looks more like an O, because I want you to be able to spell as well. So Pythagorean theorem. Well, let's just review the Pythagorean theorem. It says, in a right triangle, if A and B are the two legs and C is the longest side, the hypotenuse, then A squared plus B squared must equal C squared. So now what's going to happen is, suppose you're given three sides in a triangle. The question is, what kind of triangle is it by angle measure? Is it a right triangle? Is it an acute triangle? Or is it an obtuse triangle? Just to review the definitions, a right triangle is when there's only one angle that's equal to 90. An obtuse triangle is only one, you could also say exactly one angle is greater than 90. And an acute triangle, all three angles are less than 90 degrees. Well, the first thing we should really check is, do these three sides form a triangle? So, is it possible to be a triangle? Now, this is not the Pythagorean theorem. We have a way to check. You take the sum of the two small sides. It's actually the sum of any two sides, but you only have to check the sum of the two small sides. If that sum is bigger than the longer side, which in this case it is, then yes, we do have a triangle. 14 is bigger than 10, so we know that 6, 8, 10 definitely does form a triangle. So the question is, which kind of triangle is it? Well, let's assume it is a right triangle. If we assume it's a right triangle, and we have the sides 6, 8, 10, well, 10 is the longest side, so if that's the case, then 10 would be the hypotenuse. The other two sides are the legs. So we're going to check, does the Pythagorean theorem work? 36 plus 64 equals 100. Since 100 equals 100, we reached a valid conclusion. Our assumption of is it a right triangle is true, because the Pythagorean theorem works. So we do have a right triangle. Well, if it's not a right triangle, that means it must be acute or obtuse. So let me try three other sides. Different example. 7, 8, and 11. So first we're going to check, does it form a triangle? Once again, this is not the Pythagorean theorem. Is 7 plus 8 bigger than 11? 15 is bigger than 11. So yes, we have a triangle. The question is, what kind of triangle is it? So now we're going to assume it is a right triangle. If it is a right triangle, we employ the Pythagorean theorem. 11 is the longest side, so that would be the hypotenuse. I'm just going to put a question mark above this. I could have put a question mark here as well. If it works, then we're all good. Is 7 squared plus 8 squared, is that larger? Is that equal to 11 squared? Does the Pythagorean theorem work? 7 squared is 49. 8 squared is 64. 11 squared is 121. 49 and 64 is 113. So 113 does not equal to 121. So since the Pythagorean theorem doesn't work, we know it's not a right triangle. I'm going to take those numbers to the next page. So we know 7, 8, and 11. When we did that out, let's do it again quickly. You saw that 121 was bigger than our sum of 113. So that means it's either an obtuse or an acute triangle. So we have to figure out which one it is. Well, Let's just think about drawing an obtuse triangle. An obtuse triangle, when you have that angle that's in between 90 and 180, across from it is that very long side. So you have to think, if one side by itself, when it's squared, if this side by itself squared is bigger than the sum of the other two sides squared, well, I think that means this one by itself dominates, so that side must be stretched out. So, in this case, since the single one squared is larger than the sum of the other two squareds, therefore it must be an obtuse triangle. So if a squared plus b squared equals c squared, if a triangle is possible, then it's a right triangle, as we just saw in the separate example. If a squared plus b squared is less than c squared, that single side dominates, so it's a stretched out side, therefore it's an obtuse triangle. And lastly, if a squared plus b squared is greater than c squared, the two small sides, when they're squared, they're not being dominated by that third side squared, so therefore it is an acute triangle. You want to make sure when you do this that it's always the two small ones compared to the longer side. So let's do another practice example of this. Suppose you have 5, 13, and 12. What kind of triangle is it? Well, first thing I want you to do is let's check if it is a triangle. And here you have to be a little careful. Notice these numbers are not from small to large. So you want to reorder these from small to large. If not, you may get a false result. So we check first, is it a triangle? Do the two small ones, are they greater than the third one? 15, 12 is 17. 17 is bigger than 13. So yes, since we have a true inequality, yes, we do have a triangle. So now we're going to check Pythagorean theorem. We do leg squared plus leg squared, question mark. Does it equal the longer side, which would be the hypotenuse squared? Well, 25 plus 144 is 169, and 13 squared is 169. Since Pythagorean theorem works, therefore, yes, we have a right triangle. We can have other examples that have radicals in as well. And let me just do a couple. Here I'm just going to assume that it is a right triangle, but I'll show you a way without a calculator how to tell that it is a triangle. I can show you a way. You're not really sure, perhaps 5 radical 3 versus 10, which is bigger, but there's a way to check it out. So let's just square each number. I'm going to assume 10 is bigger. Well, we can check it out. So if we do 5 squared, and then I have 5 radical 3 squared, I'm not putting the plus sign. I just want to see which number is larger. I'm thinking 10 is larger, but we square each. So 5 squared is 25. 5 radical 3, if we get cross multiplication, you can think of distributing that square term to each, but I'm going to write it as 5 radical 3 times 5 radical 3. 5 times 5 is 25, radical 3 times 3 is 3, so 25 times 3 is 75. And 10 squared is 100. So, if you notice, when you square the numbers, that the last number, 10 squared is 100, is bigger than 5 radical 3, it's squared 75. So if a number, when it's squared, is larger, that means the initial number must be larger. So 10 is actually the longest of the three sides. Well, let's still go back to Pythagorean theorem. Does the small one squared plus the middle one squared, question mark, does that equal the big one squared? So here, 100 equals 100 again. So yes, we have a right triangle. Oh, caution here, notice the sides we did correct, and so we're okay. This doesn't really look at is 5 plus 5 radical 3 bigger than 10. There are ways to do that, but we're going to assume that is a triangle. Let's do another one. Square root of 3, square root of 4, square root of 5. I'm just going to assume that does form a triangle. So the question is this a right triangle? Do Pythagorean theorem. We assume it's right. We see if it works. I'm just put a question mark. Square root of 3 squared is 3. Square root of 4 squared is 4. Square root of 5 squared is 5. Okay, so here 7 is bigger than 5. So we know it's not a right triangle. That means it must be either acute or obtuse. Well, here, the two small sides, when it's squared, it's bigger than the third side. So I think that third side is not stretched out. So the way I think of it, therefore, it's not an obtuse triangle. It is an acute triangle. And there's something very important called Pythagorean triples. There's actually an infinite number of them. These are integer side lengths that form right triangles. Integers mean numbers that have to be positive because of lengths, first of all. So positive integers, 3, 5, 6, 7, 8, etc. So there are groups of 3, 4, 5 is a Pythagorean triple. If you have the sides 3, 4, and 5, you know there are 3 integers that form a right triangle. Well, by similar triangles, we can double these to get additional Pythagorean triples. 3, 4, 5, we can double it. 6, 8, 10, it's twice as large. If you do Pythagorean theorem here, you'll see it works as well. We could triple the initial one. So 3 times 3 is 9, 4 times 3 is 12, 5 times 3 is 15. We can keep going. But 3, 4, 5, 6, 8, 10 are very common Pythagorean triples. Other separate ones are 5, 12, 13. A bit less common though, but another one is 7, 24, 25. And another one, once again not as common, as 8, 15, 17. So how can these help? Well, if you have a right triangle, and if you know your triples, so if you see 15, 13, they ask you to find y. Well, you could do 5 squared plus y squared equals 13 squared and solve it algebraically. But if you know your Pythagorean triple is 5, 12, 13, just make sure 13 is the hypotenuse. It is, so therefore our missing side length of, we have y in this diagram, y must be the value of 12, because 5, 12, 13 is a Pythagorean triple. But where you out, which I just hinted about, even if you know the Pythagorean triple 6, 8, 10, don't fall for this. If I put 8 here and 10 here, don't say, oh, 8, 10 sounds familiar, 6, 8, 10. That can't be the case, because 6 is not, it can't be the hypotenuse, because the hypotenuse has to be the longest of those sides. So if I gave you this diagram, and I said, find x, in this case, Pythagorean triple can't be possible, so you would have to use the old approach and do 8 squared plus 10 squared equals x squared, and solve from there. And then one question. Suppose a triangle has 3 sides, 4x and 8. You want to know, find the value of x, the missing side, to make a triangle acute. Well, I want you to think about this question. We'll go over it in class. But one little thought is the missing side, maybe it's one of the 2 small sides. So we can keep the x where it is if I'm going from small to big. But couldn't it also be that the missing side is the longest side? In that case, it would be 4, 8, and x. So you may want to think about acute triangle. We know that a squared plus b squared has to be greater than c squared. Well, if it's the two smaller ones, it doesn't matter if it's x or 4, what the order is there. But if the missing side is the longest side, it's over there. And I want you to work on that. We can talk about it in class.